Hi, welcome to our electromagnetic theory course. In this video lecture, I will derive boundary conditions for dielectric conductor interface. In the previous session, we derived boundary conditions for electric field for dielectric interface. In this case, we changed it as dielectric conductor. First medium is dielectric, second medium is conductor. So let us consider electric field exists in this region like this. So electric field in the first medium is E, that is epsilon 1 or epsilon, and whereas it is dielectric, first medium is dielectric, and this one is conductor. This is conductor. This is conductor. Second medium is conductor. Let us say epsilon 2. We know that inside the conductor electric field is 0. Inside the conductor electric field is 0. That means what? There is no question of E1, E2. Only we have the electric field in the first medium. So that's why I consider that electric field in the first medium as E, whereas electric field in the second medium is 0. In order to derive the boundary conditions, we need to use three equations. First one is what? That is integral E dot dl equal to 0. One of the Maxwell's equation for electrostatic field. And another one is what? Gauss law, that is integral d dot ds equal to q enclosed. And the third one is what? We need to decompose the field component into two orthogonal components. One is the tangential and a normal. Tangential component, normal component. Tangential means what? Along the boundary. Okay, tangential to the boundary, and normal means normal to the boundary. So that is d equal to dt plus dn. In order to derive the tangential electric field boundary conditions for dielectric conductor, okay, we need to apply equation 1 for this closed path, that is ABCDA. So that is equation 1 is nothing but what? Integral E dot dl equal to 0. So for the closed path ABCDA, that can be splitted as what? A to B, next B to C, next C to D, D to A. So A to B means what? It is in the first medium. B to C means what? Covered in the first medium as well as in the second medium. C to D means what? Entirely in the second medium. And D to A means what? That is in the covered in first half is covered in second medium, and remaining half is in the first medium. So that's why we can go for this one, that is as it is in the first medium, we have the field component, that is what? E is uniform, that is tangential component of E, along AB, that is tangential component of E, that is ET, into width, that is delta W. Next coming to BC, that is ET into delta W. Next B2C, that is covered in the first medium as well as in the second medium. For the first medium, this is going in downward direction, but field component in the first medium is E. So that is the normal component, that is En into delta H by 2. Half part is covered in the first medium. So that's why total height is delta H, whereas from this point to this point is what? Delta H by 2. Next C to D. Okay, next part is what? 0. Why? That is covered in the second medium. So field component is 0, that is E is 0, as E is 0, that is 0. That is second part of this BC. Next C to D, that is in the second medium, means 0. And D to A, half of the part is in this medium, and remaining is what? First medium, that is what? Minus, sorry, here En. En is in this direction, it is minus En. Next, this part to this part is 0, that is tangential components of this second medium, that is 0. E to N is 0, E as E is 0, E to N is 0, E to E, that is normal component is 0, E is 0 in perfect conductor. Next, this part D to A, so that is in the first medium. Field component is En, that is in upward direction. Our direction is also in upward, into delta H by 2. That equal to 0. That means what? This minus En delta H by 2 plus En delta H by 2, that equal to what? Et equal to 0. Et equal to 0. Or else it implies what? Dt by epsilon is 0, that equal to dt is 0. Et is 0 or dt is 0. As Et is 0, dt is 0. That means what? Tangential component of electric field intensity is always 0 in case of dielectric conductor interface. Now coming to the normal boundary conditions. In order to derive the normal boundary conditions, we need to apply this equation 2 for this field box. Apply equation 2 this field box as shown in above figure, that is integral d dot ds 0, that is we need to apply this equation for the field box. Okay, so For the side surfaces it becomes 0, that is integral d dot ds equal to 0, whereas for the there is a contribution for the top and bottom. For the top we have what, d1 n into delta s, and for the bottom we can write this as d2 n delta s equal to q. So that is what, d1 n minus d2 n delta s by q, that equal to what, rho s. So that is what, d1 n minus d2 n equal to rho s. Of course here one thing is clear, that is d2 is 0, means d2 n is, this part is 0, this part is also 0. Finally we can write, as there is only one component, I can consider dn instead of taking d2, so it is 0, as d is 0, since d is 0 for the second medium, this is 0. So that's why we can write dn equal to what, rho s, dn equal to what, rho s. So these are the boundary conditions. I will write that conclusion here itself, that is what, we have the boundary conditions for electric field as like this, that is Et equal to 0 and dn equal to rho s, dn equal to rho s. This is for what, dielectric conductor interface. Now we will derive boundary conditions for free space and conductor. Free space and boundary conditions for free space and conductor means what, instead of taking this dielectric one, this is replaced with what, free space, and second part is same, that is free space means what, epsilon becomes epsilon naught. And what about this, Et is 0, in this case Et is 0, that is correct. Only difference in the epsilon is replaced with what, epsilon naught, and second medium is conductor, that is 0, so that's why Et equal to 0. And next coming to normal boundary conditions, in this case first medium is what, that is, as we have only one component, we can take this as, instead of d1 it is d and it is dt, and this one is dn. Okay, now apply equation 2 fill box to derive the normal boundary conditions. If I apply, we will get what, for the second medium, that means for the second medium it becomes 0, this one becomes 0, that is dn delta s equal to q, that is what, dn equal to q by delta s, that is what, rho s. It implies dn equal to rho s, means what, we can write in case of the free space conductor, for free space conductor interface, boundary conditions are nothing but what, we need to replace, that is Et equal to 0, first one, and second one is what, dn can be written as epsilon naught into En equal to rho s, that is what, En equal to rho s by epsilon naught. These are the boundary conditions for free space and conductor or conductor free space. Okay, this is all about the boundary conditions for dielectric conductor interface, and another one is free space conductor interface. If you know the boundary conditions for electric field for an interface of dielectric conductor, indirectly we have what, boundary conditions for free space conductor. Dielectric is, free space is an example for perfect dielectric, simply we need to replace epsilon with epsilon naught. Here it is what, boundary conditions for what, dielectric conductor interface. Here dn equal to what, can be written as epsilon into En rho s, whereas if it is free space, epsilon can be replaced with what, epsilon naught into En equal to rho s, that is the difference. Okay, this is all about boundary conditions for electric field for free space conductor interface, or else for dielectric conductor interface. For the dielectric, epsilon is epsilon only, epsilon equal to epsilon only, dn can be written as epsilon into En, whereas for free space we need to write dn as what, epsilon naught into En equal to rho s. This is from where, dn equal to what, rho s, dn equal to rho s, we derive dn as what, rho s. Okay, thank you.